Let's take a look now at the mean and variance for discrete probability distributions. Now, the equation for the mean of a discrete probability distribution is simply mu. And I want you to notice this is the true mean, mu. We're talking about the distribution, the actual distribution, the theoretical distribution. So this would be the population parameter. Mu equals the sum, I equals 1 to n, of xi times the probability x equals xi. This is the outcome or the observed value, and this is the probability of that outcome. So what this actually is a weighted average. The mean of a discrete probability distribution is just a weighted average where each outcome or each observation is weighted by the probability of observing that outcome. As such, outcomes with higher probability will be weighted heavier and have more influence on the value. Okay, let's take a look at an example here. Remember our coin tossing example? We tossed 3 coins, recorded the number of heads. Just as a reminder, that distribution looked like this. We could have had no heads, 1, 2, or 3 heads. Those probabilities were 1/8, 3/8, 3/8, and 1/8. So to find the mean of this distribution, we'd say, gosh, mu equals the sum. Whoops, that was pretty ugly. Equals the sum. I equals 1 to n of the xi times the probability x equals xi, which in this case would be the observed value, 0, the outcome, times the probability, 1/8. See, here's the xi. Here's a probability of observing that specific x. I'm going to add to the next one, which is 1 times 3/8. See, here's the xi. And then here's the probability of observing that specific x. Plus 2 times 3/8 plus 3 times 1/8. Now, this is the same as 0 plus 3/8 plus 6/8 plus 3/8, which is 12/8, which is 1.5 or 1.5. So the mean of this distribution is 1.5, where each outcome is weighted by the probability of observing that outcome. Now notice on this particular one, if I were to simply take 0 plus 1 plus 2 plus 3, add them up and divide, I would get 1.5. I would get the exact same value for x bar or for mu. And just as a side note, if this was sample data, then we could say x bar equals the sum I equals 1 to n of xi times the probability x equals xi. It's just the same thing, except I'm going to change this probability to be p hat, the observed, the empirical probability. Then we'd have x bar. But you notice when I add 0, 1, 2, and 3 up and divide by 4, I get 1.5. It's the exact same as what I did by calculating the long way. Now, the reason for that, and the only reason that happened, is because the probability distribution was symmetric. If I do a really quick histogram of the probability distribution, it was 1/8, 3/8, 3/8, and 1/8. See, the distribution of the probabilities is symmetric. If I had a non-symmetric situation, then this would not be true. Here's an example where I have a 6-sided dice, and each dice has the number 1 on one side, 2 on 2 sides, and 3 on 3 sides. So that means the probability of observing a 1 is 1 out of 6. Probability of observing a 2 is 2 out of 6. Probability of observing a 3 is 3 out of 6. See, this is non-symmetric. If I take a quick look at this distribution, the probability distribution is 1/6, 2/6, and 3/6. You see the shape. This is a skewed probability distribution. So let's go ahead and just find the average doing 1 plus 2 plus 3 divided by 3, that's 6 over 3, that's 2. If I were to simply add them up and divide by n, there's 3 objects here, I would get an average of 2. But what happens if I do it properly using the discrete method? Well, I'm going to write out the discrete method first by hand, and then let's jump to the calculator and take a look at how you can do it on the calculator. The mean is going to be 1 times a sixth plus 2 times 2/6 plus 3 times 3/6. That's 1/6 plus 4/6 plus 9/6. That is 14/6, which is 2 and 2/6, which is the same as 2 1/3. So that'd be 2.33. Repeat. See, 2.33, 2 1/3 is not the same as 2. We've got two different answers. So it's really important if you have a discrete distribution to do it properly using the discrete method. Now let's jump to the calculator real quick, and I'm going to show you how we could do this in our calculators. So I'm going to stat, edit, and keep in mind there's no magic button here. It's not a matter of putting in data, hit the magic button, say calculate the average. Really, I'm doing this the same method did by hand, but I'm going to let the calculator do all the actual arithmetic for me. Well, the outcomes was 1, 2, and 3. So I'm going to put that in one list. The next list, I'm going to put the probabilities in. That was 1 out of 6, 1/6. The next one was 2/6. And the last one was 3/6. Now I'm going to come over here to L3, and I took the observation and multiplied it by the probability, so I'm going to tell the calculator to do that for me. So in L3, I'm going to say L1 times L2. See, I'm up at L3, so it's going to have an effect on the entire column. And I'm telling it to multiply L1 and L2, put the results in L3. So there's my individual calculations. Now all I need to do for the average is add these up. So if I go to Stat, Calc, one variable statistics, and I'm going to do this on L3, hit Enter. I am not looking at this average. This average means nothing here. I'm using the calculator to add them up. And when I add up all those values, I get 2.33. There's the 2 1/3, just like I said it was. So the average is 2.33. The method I just followed, if you caught it, great. If not, you want to go back over and do it a couple times and figure it out. It could save you a little bit of time. Like I said, there's no magic button. It's not just going to do it for you. You still have to go through all the steps, but you can get the calculator to actually do the arithmetic for you. That's the advantage of doing that. Okay, what about the variance? The variance, sigma squared, equals the sum, I equals 1 to n, of the xi's minus mu squared times the probability x equals xi. It's another type of weighted average. That's another type of weighted average. Well, if you remember, if you look back in the previous chapter when we introduced the idea of the variance, we took the observation, subtracted from it the mean, and then squared it, and then divided by n minus 1, add all those up. Well, we're doing the exact same thing here. We're doing the exact same thing. We're taking each observation, subtracting from it the mean, and then we're going to square it. And rather than dividing by n minus 1, we're going to multiply it by the probability of observing that to begin with. So for the coin toss example, let's do it for this one. The variance would equal, the first observation was 1, minus the mean, which was 2.33. And rather than 2.33, I'm going to put in here 14/6. How about 7/3? Because this reduces to 7/3. I'm going to keep it exact rather than doing the rounding thing. So it's 1 minus 7/3 squared times, what's the probability of observing a 1? 1/6. Plus, the next observation was 2 minus 7/3 squared times, what's the probability of observing a 2? It's 2/6. plus the last observation was 3 minus 7/3 squared times, what's that probability? 3/6? Which equals, I'm not sure what it equals. Actually, you can probably do that in a calculator and come up with a value. But that's the process for it. So let's go ahead and jump to the calculator and actually figure that out. I'm going to go back to the editor. And this time I'm going to clear out L3. And now I'm going to tell L3, I'm going to actually program into L3 that process I just did. Xi minus the mean. Well, if I put in parentheses, where's the Xi? So Xi is in L1. So L1 minus, well, the mean was 7/3, correct? So 7 divided by 3, parentheses. I need to square it. And then I need to multiply that by the probability. Well, the probabilities are in L2. And this is going to store each one in L3. So hit enter. So there's the individual values if I were to actually work this out by hand. But if, once again, if I go to Stat, Calc, one variable statistics, and complete the one variable statistics on L3, again, all I'm interested in is the sum. The sum is 0.5556. So this is actually going to be 0.5556. And just as a reminder for the standard deviation, sigma is equal to the square root of sigma squared. So sigma is going to be the square root of 0.5556. That would be the standard deviation if you need the standard deviation rather than the variance. So quite frankly, quite often, or most of the time, we work with the standard deviations, not the variances. We just use the variance as a method of calculating, take the square root, have the standard deviation. That's what we're going to have working with.